Hi everyone, this is going to be an introduction to the definition of a determinant map of a square matrix. Also, it's going to give you a motivation and some basic results that it's related to the whole motivation and definition of a determinant map. Well, at the beginning, this is a linear algebra subject, of course. At the beginning of the linear algebra, we're introduced with the system of linear equation. This is how it starts, the elementary linear algebra. Then to solve that system of linear equation, we use this Gauss-Jordan elimination method, which is eliminating one variable at a time. And after we learn the full techniques of this Gauss-Jordan elimination, and we focus on, not necessarily focus on, we introduce the invertible matrices and a characterization of all invertible matrices. Then at that point, we introduce not this algorithmic, this Gauss-Jordan elimination method is a very algorithmic method, but at that stage, after we learn this, we kind of introduce more algebraic, more straightforward kind of formula of this inverse invertible matrix and its inverse, using something called the determinant. And when the determinant is introduced, it's rather usually it's given straightforward definition, and from that we prove lots of things. And that's usually how mathematics is introduced. But I think for this determinant map, it better have nice introduction. So students, it's very, very complicated algebra involved, and students are usually overwhelmed by the definition itself and then how it's connected to all the properties. So I think it's worth approaching in a slightly different way so the students are not kind of knocked down by the heavy loads of the determinant algebra. So that's usually pretty much the main purpose of this video. So of course we're going to start with the 2x2 cases, and I assume you've known these 2x2 cases. So let's start with this inverse of 2x2 matrix A, B, C, D. By definition, of course, this inverse is looking for this matrix, and under this matrix multiplication becomes so-called identity matrix of size 2. And if you apply that elimination method, this is the answer we get. You multiply C there and multiply A there and subtract, and then it's going to eliminate x variable from the second equation and solve for y, and then use that y as solution for y and then substitute here to get A. And it turns out the inverse for 1, 0 and 0, 1, that's the equation we're going to look for, solve. It turns out this is the matrix. So we basically use this elimination method, and of course using this nice 2x2 sides, and we're going to build up to the 3x3 sides and kind of write down the nice formula. And after we strip off these matrices, the patterns goes inside the inverse formula. The formula for the inverse of a square matrix is kind of neat. So what is this determinant? This determinant is this denominator that showed up in this particular formulation. Turns out there is just the polynomial in ABCD showed up when you try to write down the algebraic closed formula of the square matrix. There's always all the polynomial entries all divided by this nice common polynomial. So the common denominator that showed up is called the determinant. So in this case, the determinant will be this AD minus BC. So I wrote it up here in the next slide. Next thing I'm going to introduce is that, so we've seen the inverse formula, but let's see how we're going to use that inverse formula, the inverse matrix, to solve a general system of two linear equations in two variables. So in matrix notation, it looks like this. A, B, C, D, so that makes you AX plus BY equals S, and CX plus DY equals T. those two system of two linear equations can be put into one single matrix equation like this. So once we introduce this matrix algebra, it works just like this is one and one coefficient. Here's a one entity called a column vector and equals another column vector. So we can do multiplication algebra just like we do with this simple number equation like ax equals b. Now here matrix A times a vector x equals like vector b kind of relation. So what we have to do, you multiply the multiplicative inverse of this matrix, which is what discussed a minute ago. So here it is, that if I multiply the inverse to that side and that side, then these two inverse and this matrix cancel. It becomes identity matrix. So invisible identity matrix is here in xy, and that inverse is multiplied at here. So I'm going to next separate this x and y and introduce what is called something called the Cramer's formula. Cramer's rule. So here it is. If you look at the x part, that will be the entry of the this column vector. So if you look at this right hand side, the first entry would be ds minus bt. So that's why you see st minus bt, and the determinant is an abbreviation of this ad minus bc down there. So that's what x is going to be. Cramer's rule formulate this answer in the following way, and it turns out this pattern is true for all the higher when we have more entries, bigger size of the matrix. So st minus bt seems like another determinant of matrix, and you can organize an st there and bd there, and then you can see the determinant of this matrix sbtd is sd here minus bt. Okay, so that's what this is. So we can write it as x as 1 over determinant of the coefficient matrix times, this is times, determinant of kind of ABCD, but first column is replaced by the right hand side vector of the equation. Okay, so this turns out to the kind of similar pattern for y as well. So here's y. If you look at y there, the second entry, and this is going to be negative sc plus at. So it's negative sc plus at and 1 over the determinant, which is this ad minus bc. Let's see if we can organize this second factor here as a determinant of something. Then it turns out we can do the similar thing, that ABCD appeared here. Instead, the second slot is replaced with this right hand side vector st. Then you can see AT positive and SC negative. So these two things are equal to each other, where this determinant is determinant of the coefficient matrix. Now we're about to enter 3x3 cases, and using that 3x3 cases, I'm going to motivate how this determinants thing is going to show up. I'm going to show how this one shows up, and then from there, from the formulation of the definition of the determinant, then we're going to kind of introduce nice theorems and property just using this type of formulation, and then using that eventually come back to this Cramer's rule, so kind of close up this introduction of the determinant as a part of the introduction of the inverse of a square matrix, and then close up with the Cramer's rule of more entries, bigger size of the matrix. So here's a 3x3 case. So I denoted the entries in this way. First row A's and second row B's and then third row C's, and we're looking for this matrix. When you multiply from the right, then it becomes identity matrix, which is 1 0 0 0 1 0 and 0 0 1 in its column of a matrix. So we can look at one at a time, because this matrix equation is actually a combination of vector equations. So this matrix times this column vector equals 1 0 0. If you think about it, what we do with this column vector x, y, z, we actually multiply to this matrix, and it must equal 1 0 0. So that's what this matrix multiplication breaks down to. So in our textbook it's called partition of matrix multiplication. So we're looking at three different equations, x, y, z here, z equal to 1, 0, 0, which is written here, and later we'll look at different x, y, z, and z equal to 0, 1, 0, different x, y, z, z equal to 0, 0, 1. The trick we're going to pull out is we're going to use this 2 by 2 case result we just introduced. So this 0 and 0 in the second and third equation, third line rows, it turns out a nice thing. So we can isolate. So what we're going to do, we're going to isolate this x and y. X variable go multiplied here, and y variable is multiplied there, and z variable is multiplied there. If you just consider this equation as an equation of y and z, and then consider this b and b1x and c1x as a constant, move it over here, something nice happens. So here's the situation. We look at the b2y and b3z, c2y and c3z, and the other b1x and c1x is moved over here. So from here it's just a 2 by 2 matrix equation where x is considered as a constant, and we're going to call the determinant of this coefficient 2 by 2 coefficient matrix by d1. So d1 is this matrix right there, this 2 by 2 matrix that contains these two entries, c2 and c3. Okay, that's d1. And we've seen the Cramer's rule, so this is y and z variable is involved here. So y is going to be the 1 over the determinant times the determinant of this coefficient matrix. The first variable, first slot column, is replaced by this right-hand side of the equation, negative b1x, negative c1x, and b3 and c3 is the same as the coefficient matrix. The same for the other part. The z is the second variable for this 2 by 2 equation, and 1 over the determinant of the coefficient matrix times the determinant of this coefficient matrix, where the second slot, second column, is replaced by this column on the right side of the equation. So that looks like this. So let me write it over here because I need a space down there. And x and x is common, and if you think about the 2 by 2 matrix and its determinant map, it's not hard to see this x and x is a common factor can be pulled out as a single copy of x. And same here, x and x can be pulled out as a single copy of x. And the same as negative x can be pulled out. But if you look at the second column here, because its order is slightly different, when you pull out x and negative, this negatives kind of cancels. But first I did this x factor out, x is out and x is out there. Then we try to recognize these determinant of the second factor as in the context of how we label this d1 and d2. That seems like it's possible. So let me show you how we're going to label this other coefficient involved in here and there. So this is how we do it. We call it d1 because we it doesn't include the first column. We're going to call that matrix b1, b2, c1, c2, and it's determined by d3 because it doesn't involve this third column. d2 we're going to call that involves b1, c1, and b3, c3 by d2 since it doesn't involve the second column. If you do that, this b1 and c1 and b3 and c3 looks like this b1 and b3 and c1 and c3. That's exactly the determinant of d2, but because of this negative, if you calculate that simple 2 by 2, you'll see that this is negative d2. Negative d2 here, determinant. Which I wrote it here, x over d1 and negative d2. But if you look at it here, this one is a b1 and c1 and b2 and c2. So b2 and c2 is here, and b1 and c1 is there, but it's kind of opposite order. So if you rewrite it, b1 and c1 in here, b2 and c2 there, and it turns out, if you compare this cross multiplication, the simple 2 by 2 determinant map, it turns out this one is actually equal to d3, which I'll skip, but you can pause the video and check yourself. And anything that gets more complicated than this, we will carefully argue that why whenever the sign is involved in here. But here I think it's 2 by 2, and it's very simple, and you can calculate straightforward. Okay, now I wrote this y and z over here so that I can do the x part. We want to solve x and y and z, and because of this 0 and 0, I'm isolating x, and we wrote b and y and z in terms of x like this, and it is like linearity is there, x is still multiple because of the 0 factor there. Okay, that's why we chose this y and z, so that it has nice multiples show up. So let's think about the equation that we didn't touch. Is the first one, a1, a2, a3, and with the variable this looks like this: a1x plus a2y plus a3z equals 1. So let's substitute what we know about y and z in terms of x, and these are very concise form, compact form of the solution. So then y's part that we use is x d1 minus d2, it's a multiple, and z we have this x d1 d3, and that goes there. So x is all common, and d1 happens to be the common denominator for the two terms, so let's use that. Then it factors out like this: x is factored out, let's factor out d1, and these had d1, but the first term didn't have d1, so you must have the d1 up there. Other than that, it's easy to see how this factors, and x equals 1. So let's solve for x. Then it becomes like this, right? d1 was down there before the numerator, and whatever that long thing is down there in the denominator. Okay? So that's what x is, and the good thing about this x is this time this x does not involve y and z. Before y and z involved the other variable x, so x here is truly the solution. So if you look at what d1 is the matrix 2 by 2 matrix that of this one, and d2 was a 2 by 2 matrix that involves first and the third column and so on. d3 is first and the second column. So that's the completely given by that coefficient matrix of size 3 by 3. And if you think about the 2 by 2 case, the solutions has nice polynomial form, except there's a common denominator that showed up in the inverse of a 2 by 2 matrix, and the denominator also was polynomial. So it's the same phenomenon up there in the numerator as nice polynomial of coefficient matrix, and the denominator is also a polynomial, and I hope that this appears as a common term. But that's the motivation that appeared, so we're going to call that determinant. And we need to argue a little bit more about this one, but that's kind of motivation. How are we going to define the determinant of 3 by 3 matrix using this type of shape of the solution, and denominator shows up. And this is really the definition of a determinant of 3 by 3 matrix. So I want you to look it up here, and this is the item that I want to show all together. Okay, before y was in terms of x divided by d1 times negative d2, but now x is this one, d1 divided by, now it's simpler d, so x over d1 will be simply this 1 over d. And z is x over d1, but again, d1 is here and x is there, so x over d1 will be simply 1 over d. That's why we have this shape. So let's see all of these together. So this is how it looks like. It's quite consistent with this notation. It's quite consistent looking, symmetric looking shape. D and D and D all as a common denominator showed up. And then d1 and d2 and d3, these are the coefficient matrix again, but it's also polynomial. So in this form is kind of, we can compare the solutions of the inverse matrix of the 2 by 2 we did it earlier, and the denominator is all common. So that's the motivation, that denominator is going to be called the determinant. Now we are here in a position where we can define the determinant of a 3 by 3 matrix. And from there, I think it kind of makes sense, and we're going to define 4 by 4 matrix, a determinant of 4 by 4 matrix, and so on. But this is actually quite general enough to you see that full picture. So when we see this 3 by 3 matrix, what we call the determinant is this one. That was the denominator. So let's organize this one so that we can understand what this is. This A1, A2, A3 kind of appeared as a coefficient of this D1, D2, D3, but these A1, A2, A3 are the top rows. So the way we're going to define the determinant of 3 by 3 matrix is going to be top rows become the coefficient. But it's the odd thing is that A1 is picked up, but there's this negative A2 and then there's a positive A3. So sign changed, alternated. So if you look at the 4 by 4 matrix and try to define the determinant, maybe we're going to go through exact same calculation, but if you just focus on the result, the common denominator, it looks just like this. And indeed, this alternating sign phenomena happens. So if you look at 4 entries in the top row, then you're going to have first entry, and negative of the second entry, and positive of the second entry, and opposite sign of the fourth entry, but opposite is a better word. So that's what happened in general. So let's think about this D1 and D2 and D3. D1, we labeled it here. If we are dealing with A1, you kind of isolate this columns and row. You remove this row and column that contain A1. And what you're left with is this 2 by 2 matrix, which is B2, B3, and C2, C3. So determinant of that is called D2. Now let's look at A2 with this alternating sign in front of A2. Here's A2. I want you to remove row and column that contains A2. Then you're left with B1, B3, C1, C3, the 2 by 2 matrix after you remove the row and the column. Then determinant of that is D2. Let's see if that's consistent with the third one, A3 here. A3 is there. So if you remove the row and the column, and you're left with this 2 by 2 matrix right there. And that was indeed the definition of D3. The determinant of that 2 by 2 matrix was the D3. Okay, so this is how it's defined. Once we have this definition of a determinant of 3 by 3 matrix, and then you can think about 4 by 4 matrix, and that all makes sense. So, but before we move on to, because it's quite general enough, I think you kind of have an idea to a 4 by 4 case, but I'd like to touch on an important property that falls right away, very fairly immediately from this shape, which is a linearity and some skew symmetric property. And that's very important. With this definition, that property falls out right away. And having that algebraic property is really, really powerful tool to handle this complicated algebra.